Welcome back. This is week number 11. We're going to do some examples. Don't have a lot of examples for accelerometers, which you did, but I do have some for some of the other problems. All right. So first, let's read the thing. This example illustrates how an independent measurement of acceleration can provide a measurement of a transducer's mechanical properties. An accelerometer is used to measure the oscillation of an airplane wing. There's an airplane, there's a wing off the airplane. It's got an engine right here, so he got a little accelerometer here. See where this, we're going to measure the thing. Okay, enough. The plane's engine is operating at a speed of 6,000 RPM. So that's the thing that's generating motion, and so that's 628 radians per second. At this engine speed, the wing is known from other measurements to be experiencing an acceleration equal to 1g, right, or equal to 9.81 meters per second squared. And that's going to be equal to, from our way of thinking, y double dot. All right, so this is the base motion, and now we're going to see what the accelerometer picks up. The accelerometer measures an acceleration of 10, right? So that's going to be z double dot is what comes out from here into the machine. It's going to be 10 meters per second squared. So you can already see there's 9.81 and then there's 10. So the true one should be 9.81, but the meter itself measures 10. If the accelerometer has a mass, right, of 0.01 kilograms, and they can be quite small, so that's reasonable. Moving mass and a damped natural frequency, right? So of 100 hertz, which is 628 radians per second, right here. The difference between the measured and the known acceleration is used to calculate the damping and the stiffness parameters associated with the accelerometer. So we're kind of going backwards right here. So first thing, let's do z double dot over y double dot. Let's see what the error is. 10 over 9.81 is going to be equal to 1.0194, which is approximately 2% error. Right. Well, that's going to equal, and we're going to go back and use these terms right here. Use this equation right here. This is going to be the relationship between these two right here. That's going to be the difference between there. So the z double dot divided by y double dot is going to be equal to this. Right, so I just want to make sure you knew where I was getting the equation from. Square root of r, well, not r, 1 minus r squared, squared plus 2 squiggle r squared. And as I mentioned in the other video, that looks really familiar in a lot of ways, but there's some subtle differences when using an accelerometer, as I mentioned in the previous introduction video. So our goal is to find both the R and the or the combination of R and squiggle, the damping ratio, that will generate this amount of error, and then we can reason out what the other's going to be. At this point in this particular problem, we're kind of doing a one-off, and that's the way that I think of some problems. Like, I don't think this is like a common thing to be asked, but we can use the information that we're given and break this thing apart. So first thing I'm going to do is I'll rewrite out this equation and square what I can. R squared squared plus 2 squiggle r squared is equal to 1 over 1.0194, and then we can square that, and that comes out to a number 0.9624. And maybe you can save this for later, right? Now we want to find, we need squiggle right here. So we can try to make this argument here. We know that R is equal to omega F over omega N, but we don't know omega N. We know omega F, which is going to be the 628. We do know omega D, though, right? But that's the damped one. You can't just simply substitute those. But we can write out what the equation is for it, which would be omega D divided by the square root of 1 minus squiggle squared. That's because we know that omega D is equal to omega N times 1 minus squiggle squared, right, by its definition. So we've just reversed that thing around, and now we have omega F over omega D, square root of 1 minus squiggle squared. Well, it just so happens that we have a magical, this is why I'm calling this the one-off type of thing, right? So because we have that, and we know that that right there happens to equal that, it turns into 1. I suppose we could, it didn't need to be 1, but it works out pretty well that way. So therefore, we could go and use that R is equal to the square root of 1 minus squiggle, or we could say that R squared is equal to 1 minus squiggle squared, or alternatively, squiggle squared is equal to 1 minus R squared. Now, coming back to the equation that we saw up here, we have that is very close to this, and this is very close to, oh, excuse me, no. Okay, so we could place those back in there. So what we essentially could do, let's see, we can solve for squiggle this way, right? So we're going to replace this guy right there with a squiggle fourthed right there, plus 2 times, but it's squared, so we can go 4, and then take a squiggle squared, and then take an R squared, which we happen to know is equal to 1 minus squiggle squared, if you're following me. And now we got 0.9624, right? So now we can write this out again, collect some terms. Let's change it to dark red. So we're going to have 3 times squiggle to the 4th minus 4 squiggle squared plus, and then 0.9624, and we have what is in essence a quadratic, and we can use the quadratic formula, or Wolfram alpha. And what we end up finding is squiggle, the only root to this is 0.5613. In other words, so this is the only root of this thing that makes any kind of sense. The others are negative, or they're outside of the range. So they're greater than 1, which we can't have. So what we're left with now is the ability to now find the natural frequency, right? Because we could, from here, knowing the squiggle and knowing the damped natural frequency, we are able to get the natural frequency. So let me go blue. So we go omega n is equal to omega d divided by the square root of 1 minus squiggle squared, or 628, as we were told, and square root of 1 minus 0.5613 squared. And so now we get 758.8 radians per second. We knew the mass, and we know that the natural frequency is the square root of k over m. So we can find the k by taking the mass and multiplying the natural frequency squared by it. So the mass was 0.01, so right, 0.01, and we have 758.8 squared. So now we can get the stiffness, 5,758 newtons per meter. And that's part of what we need. And we also, we can find the critical damping from this. Critical damping is 2 the mass times omega n. So we can go 2 times 0.01 times 758.8. And that turns out to be, oh, I did it in one step. So let me go here. Well, we know the damping factor. Oh, what's going on here? I can't. Oh, no. Why won't they let me? There you go. Couldn't erase all of a sudden. The accelerometer in my pen wasn't working. That's how I think that's pretty sure that's how that works. We know that the squiggle is equal to C over CC. So we could find C by taking squiggle times CC, which means to take squiggle times, and recall that this was 0.5613. Would have normally been 0.7. We could have assumed it was 0.7, but it is, obviously it isn't. Times 2 times the mass times the natural frequency of 758.8. And we get a C equal to 8.518 Newton seconds per meter. And so this is maybe something that would work out. You kind of did expect that damping ratio to be in the 0.7, considering how we see the curves work out. So I'm going to stop and create a new video now. And so this was example 1. Example 2.6.1 out of the Inman